Welcome to a bootstrap lesson on the use of Arduino. Please feel free to pause and replay whenever you like to. Pen and paper are not required. No prior programming background is required. Before we begin, it is highly recommended that you be well versed in certain basic knowledge of electronics and circuits. The understanding on the use of the breadboard and basic coding logic will speed up the learning process. The Arduino is a low-cost microcontroller board and user-friendly programming software that allows DIY electronics-based projects to take off rapidly. The project originated in northern Italy by a group of friends who were tasked to create a user-friendly tool for students to rapidly prototype an electronic circuitry. The name Arduino takes that of the pub there they love, Bar di Re Arduino. So, what's the moral of the story?
I like beer cause it is good. I drink beer because I should. Beer is good. Beer is good. Beer is good.
Here is an important overarching simple concept in the world of Arduino: inputs and outputs. Basically, the Arduino takes in inputs, either digital or analog, from the environment and creates a desired output like making a sound, moving motors, lighting up LEDs, or even just storing data. Much like how the human biological system does. The process is very systematic and chronological. The kinds of outputs or inputs that are desired are determined by the electronics available and the codes written by the user. The user gives Arduino its brain via coding, and the electronics gives Arduino its sensory and reactionary capabilities. There are many types of Arduinos available for different users. For example, the Arduino Fio is suitable for Wi-Fi usage. The Arduino Mega provides a huge array of pins, about 54 digital inputs or output pins, and the DailyPad is made for wearable technologies. There are many more boards for other types of users. The most common variation is the Arduino Uno, which we will be using in this video. Generally, an Arduino board contains the following generic items. Firstly, microcontroller. It makes everything work. Your interface and capabilities of the Arduino depends on this. It processes your codes and executes them using the concept of inputs and outputs. Second, digital pins. These are pins that receive digital inputs or generate digital outputs. Each pin takes two values, high or low. Each high signal is represented by a 5 volts DC output, and each low signal is represented by a 0 volt DC output. Some of the digital pins have a wavy line symbol on them. These are called the PWM digital pins. These pins have special abilities that allow them to operate with duty cycles as shown in the graph. The percentage of duty cycles represent how long the pin will be in an on or high state within a cycle. By cycling a digital signal off and on at a fast enough rate with a certain duty cycle, the voltage output averages and appears to have voltages between 0 and 5 volts. These pins are usually used for varying motor speeds, dimming LEDs, generating analog outputs, audio signals, and modulated signals. Third, analog pins. These pins read voltages within a circuitry. For example, from analog devices like LDRs. The microprocessor will help convert these voltages into readable and usable data that can be operated on in your code. Fourth, crystal oscillator. This component helps the Arduino to keep track of time. Fifth, USB connection. It helps to power up the Arduino as well as transfer data from the computer. Sixth, power jack. It is an optional external power source to power up certain components that require higher voltages like a servo motor. Having an external power source enables the Arduino to be portable as well. Seventh, ICSP header. It allows users to code via C++ directly to the microprocessor without having to remove the microprocessor. Eighth, reset button. Ninth, indicator LEDs. For example, transmission and receiving indicators. TX, RX indicates that your Arduino is transmitting or receiving data. Other components like the op-amps, MOSFETs, PWM signals, and voltage regulators that makes up the Arduino will be learnt in your EPD course, Circuits and Electronics. Each board comes with its own specifications. For the Arduino Uno, here are the specifications. You can find the full specification sheet at the official Arduino website. Please take note of the output and input current or voltage, as you may need to consider them when you wonder why certain components can be powered directly from the Arduino pins and why for others you burnt these components. The Arduino Uno is sufficient to kickstart your prototyping journey. Now that we know roughly how an Arduino works, let's download the program into our computers. The program enables us to communicate and control how the Arduino should behave based on the electronic circuit that you will be setting up. Please skip the following segments if you have already installed Arduino in your computer. For Mac users, the steps should be very similar and intuitive. Step 1. Type arduino.cc in your web browser and hit Enter. Step 2. Head towards the Downloads tab, and there you will easily find the Arduino program and the respective downloads for the OS. For our case, as I'm using Windows, I will download the application for Windows. I will pause the download process until the next pop-up appears. Ta-da! We have the latest Arduino program installed. If you have a pre-existing program, you may also receive notifications for updates from the Arduino group at times. Just update accordingly. But wait! Sometimes we do not have the driver for the actual microprocessor installed. You can find this in the drivers folder under the original Arduino directory at Programs file, or you can plug in the USB directly along with your Arduino and download the driver from the web as shown. Now, let's do a quick test on it using one of the simplest examples, the blinking LED code on pin 13. Arduino has a pre-existing LED, L, beside the TX, RX LEDs. You do not need to change the code. Your surface mount LED should light up and off as shown. To connect your components and sensors with the Arduino, you need wires and a circuit layout. You have to know what is a parallel or series connection. To quickly connect the circuits without soldering any connections, we use a breadboard. The breadboard gets its name literally from boards where bread dough is kneaded or sliced. Circuit components are mounted on these boards and connected via point-to-point connection, where connection nodes are made of nails. In 1960s, people used a technique called wire wrapping, where they wrap wires around conductive posts that are connected to each other in series and separate lines. The interface has been improved to a plug-and-play system. So, here's the breadboard. Inside the breadboard, there are conducting strips in the form of rows and columns. At every point in the strip, the potential is the same. Whenever you insert an end of the component into a hole, it takes up that potential of the conducting strip. If there is a potential difference between the two ends of a component, current will flow from a higher potential to a lower potential. For the power rails, conducting strips are located at both ends of the breadboard vertically. Some breadboards don't have power rails, but only horizontal terminal strips. Nonetheless, all kinds are usable once you know how they work. Sometimes there are gaps as well, which separates conducting strips from each other. Independent conducting strips has independent voltage potentials. To assist users, sometimes there are positive and negative symbols at the power rails. These symbols are used as guides for you to create a power bus or line and ground bus or line, because you will easily need to tap on these potentials in your circuit. For those who know soldering, basically, connecting wires into the same bus is similar to having the ends being soldered together. The difference is that you can easily remove the connections by plugging the ends out. To connect your components in series, ensure that only one end of the components is connected to another end of the components in the same bus. The free ends of each component will then connect themselves to different potentials for current to flow through both components. Now, let us visualize how the current will flow in the breadboard. When you connect your components in parallel, the current splits into the various components that are connected to the same potential. As such, parallel components can be easily connected by connecting the ends of both components to the same hole. The potential difference across each component should be the same. Now, let us visualize how the current will flow in the breadboard. Commercially, there are various types of breadboards. Just note that when there is a separation between rows or columns, most likely the individual segments are not connected to each other. For our example, we assume the power buses and ground buses are all connected. Here are some tips and comments when using the breadboard. Alright, now that you have the Arduino program, know some stuff about circuitry, breadboard, and Arduino's input and output pins, it's time to code. Don't fret, the guys in Arduino have made coding as simple as ABC. They even have example codes pre-built in the Arduino program in your computer that you can easily try. For basics, there are 3 things in your Arduino user interface to take note. Firstly, what you see here is a scripting page where your codes are written. They term it as sketch. Secondly, you also have a serial monitor where you can print live serial readings that your Arduino is taking from the sensory components. Basically, Arduino reads voltage changes, which are represented into numbers you see when you use the serial.print related commands to show the readings in the monitor. Next, you have your toolbars where you can get great example codes, edit presets, import libraries and other advanced stuff which will not be covered in this course. One tip in code learning would be to double left click a code, right click and find in reference to know all about the code. There are examples too. In Arduino, the following codes are commonly used. Pause here to take a rough read on what each function does. We tend to use these basic commands, so please get used to them. Please note that those that are underlined are meant to be replaced with the appropriate content when coding. Let's take us through a simple blinking LED sample setup procedure to familiarize with some of the codes. Before coding, we set up an external circuit as shown. A resistor of certain value is required to limit the current to the LED when 5 volts is applied. A typical LED can take a maximum of about 20 mA. We will not want to exceed that. For our case, we use a 330 ohms resistor and digital pin 10 for our voltage source. We set up the bare minimum structure for the code under File, Examples, Basics, Bare Minimum. This example gives me the minimum code needed to start an Arduino sketch. It consists of a single run void setup to initialize the program. Any code that is written in here only runs once. It also consists of a void loop, which is where your code runs repeatedly within this segment. Your main code for your operation lies in here. Let us set our definitions at the top by using the integer operator int. We usually define the variables at the top away from the void loop function because we would like to only run this once to form the global variables, i.e. variables that doesn't change, unless you reassign it later on. Defining variables at the top also makes it more structured. In this case, we shall name the integer 10 with the variable name LED. By defining LED as the integer 10, we can later on make a more comprehensible code where we use the name LED instead of the number 10 when doing operations to the digital pin. We will use digital pin 10 to operate the LED. You will appreciate the definitions later on when you have more components to deal with at different pins. Remember to include the semicolon after each line of code, or else it will give you an error. We will now set up the digital pin 10. By default, all pins are set to digital input, where there is high impedance at the pins. As such, we need to make digital pin 10 as output in our case to lower the impedance and provide a proper output DC voltage of 5 volts with sufficient current to power the LED brightly. We set the digital pin 10 to output by using pin mode. For structure's sake, we can write the pin mode under void setup. Similar to defining variables, void setup also only runs once in the code since it is not under the void loop. We are now ready to execute the blinking code. To blink, we need a high output to supply a current to the digital pin for certain amounts of seconds, then low output to cut the current off for a period of time. We then cycle through the code to create a blinking effect. To execute this behavior in our code, we use the digital write function to generate the output of 5 volts, then the delay function for a few microseconds. Next, we use digital write again, but with a low output of 0 volts and delay for a few microseconds. In our case, we use 1000 microseconds for our delay, which means 1 second of high and 1 second of low. We can tweak this number within the delay function to adjust the blinking rate. The cycling will occur naturally since we have written the code under a loop, void loop. To upload, simply click on the upload button. You may wish to click on the verify button before clicking on upload to check your code, but it does not matter. Upload button automatically verifies for you. Well done! You have come far to reach here. By now, you should have the knowledge required to start your Arduino journey. Congratulations! But if you do feel insecure or unconfident of doing your own Arduino projects, do not fret. The more you practice, the better you get at it. To ease you into this situation, we have 3 sample projects. Each project is carefully selected to expose you to different aspects of using the Arduino board. The understanding of the content before these slides are important. Do return back to the previous slides if you have skipped them. Let's go! Yay! Let's kickstart your first Arduino project with something exciting. We will be using an ultrasonic sensor to detect an object at a distance of 4 cm away. This will be the input stimuli, and the Arduino will notify the user by lighting up an LED for its output. You will need an Arduino microprocessor, jumper wires, a 330 ohms resistor, an LED, and an ultrasonic sensor. We will be using an ultrasonic sensor, HCS SR04. The sensor operates on 5 volts with a range between 2 cm to 400 cm, resolution of 0.3 cm, a frequency of 40 kHz sound wave, about 2 times higher than a normal human's hearing, a cycle period of 50 milliseconds, which is the amount of time you have to wait between measurements, and a sonic burst of 8 cycles each time you initiate the transmitted signal. For connections, we connect the 5V power source to the VCC and the 0V to the ground. For our case, we will be using digital pins 12 for trigger pin and pin 11 for the echo pin. Before you use a component, you should already know how it works by checking its datasheet to know how to use it. The trigger pin initiates the introduction of sound waves when we give a 5V high digital output. A sonic burst of 8 cycles is produced towards whatever that is in front of it. Almost instantaneously, we also use the inbuilt Arduino command pause in to give a voltage to the echo pin, where the echo pin will remain high until it receives an incident wave that causes it to turn low. The commands enable the Arduino to start timing until the echo pin turns low. The incident waves hit the object and get reflected back to the receiver. By timing the time it takes for the echo pin to turn low, we are actually measuring the time taken for the wave to travel to the object and back. Note that the distance traveled is through D and not D. We then use the normal speed formula to calculate the distance of the object from the sensor. Now, let's set up the circuit.
Welcome to the Mastering Arduino tutorial series. Today, we are going to be looking at an ultrasonic sensor. When an object is near, the LED will light up, and when an object is far away, the LED will turn off. Let us begin. To first use any device, you must first power it. And to power the device, let's connect the 5V from the Arduino to the breadboard. This is with the red wire. Next, we connect the ground from the Arduino to the breadboard. After which, we pick up our ultrasonic sensor and get ready to connect it to the breadboard. Likewise, we need to power this device, and to do that, we first connect the ground from the breadboard to the ground of the ultrasonic sensor. Next, we connect the 5V on the breadboard to the VIN or VCC on the ultrasonic sensor. In order for the ultrasonic sensor to communicate with the Arduino, we need to connect two more pins, the trigger pin and the echo pin. For our code, this will be connected to pin 11 for the echo pin and 12 for the trigger pin. We made it such that when the object is near the ultrasonic sensor, the LED will light up. The thing to note about LEDs is that you have to connect a resistor in series with it instead of connecting it directly to power. And in this case, the power from the LED will come from the digital pin 13 from the Arduino.
Here's a circuit layout of the assembly that we had just made. Pause here to ensure that you have your circuit properly laid out before proceeding. Last but not least, here's the code that we have used. We have included the link to the code below this video, where you can copy and paste it in your Arduino program and upload. It should work. Here are some points to note. 1. Define a C programming syntax to define a pin, similar to in function. 2. Long. Similar to defining variables as integers, long allows more bits, meaning for storage for higher values. For example, the speed of light requires the variable to be categorized as long. 3. Serial begin. Because we will be printing data into the serial monitor, we have to establish this mode of communication between the Arduino and the serial monitor. Unless otherwise specified, we use a typical setting, 9600 baud rate. 4. Pin mode. As mentioned, if we are dealing with digital pins, we have to set the pins as inputs or outputs. Actually, we do not need to define the echo pin as input because all pins are inputs by default. However, we shall define it here just in case. 5. Here's the main code. We off the trigger pin, then impose a high and low to it to produce the sound wave pulse. At the same time, use pulse-in to initiate the timing. Pulse-in will produce a number, and that number represents the time. We assign the variable duration. The distance is calculated using the formula. In our formula, we wrote it explicitly to show that we are using the speed formula. For some other datasheets, they have a constant and it is derived similarly, but maybe with some estimations. So don't worry if your value of the constant differs slightly. 6. If. Here, we need to process the information, so we impose a condition that the Arduino has to know before lighting up the LED. For our case, I like the condition to be lesser than 4 cm for the LED to light up. Within the condition is the action. To light the LED up, we use digital write to generate a 5 volts DC output to the LED resistor circuitry. We also need to define what happens when it is not less than 4 cm. For our case, if it's more than or equals to 4 cm, we like the LED pin to turn off, so we use the else function. 7. Serial print ln. For a more user-friendly approach, we also want to know what the distance is when we are currently monitoring. So we do a serial print in our serial monitor. We impose a delay after the print so that we can make the prints eye-friendly. Upload time! Now, let's test that everything is working.
Here's the test to see whether the code fulfills its function. What we would like to observe is the lighting of the LED when the card or object is too near the ultrasonic sensor. Our threshold distance was set at the 4 cm mark. I will now move the card with increments of 1 cm or half a cm towards the threshold value. As you can see, there is no lighting of the LED yet. Come on, let's get closer. At the 4 cm mark, the LED starts to blink. The reason behind that is a slight inaccuracy of my hand to hold at the 4 cm mark. Further beyond that, the LED actually lights up.
Look at what this distance range finder can do in real-life applications. Here's a video of how the ultrasonic sensor can be used to notify the blind of obstacles. Project 2A. Here, you will be using a photoresistor whose resistance decreases with increasing light intensity to create an automated lighting in the dark device. This is a very simple but applicable tutorial. We will be using inputs from a changing voltage in a voltage divider setup using a photoresistor and a 100 ohm resistor. The voltage changes in different light intensities because of the photoresistor. The output will be a simple LED. You will need an Arduino microprocessor, jumper wires, 100 ohm resistor, 330 ohm resistor, an LED, and a photoresistor which is a light-dependent resistor. Now, let's set up the circuit. We will guide you through.
Today, we're going to be doing an LED circuit. What's going to happen is that this circuit will light up the LED when it's dark and will turn off when the light is bright. To do this, we'll be using the Arduino. Before we use any device, we first need to power it, and let us power the breadboard by connecting the red wire to the 5 volts of the Arduino to the breadboard. Next, we connect the ground of the Arduino to the breadboard. This will set up a voltage bus and a ground bus on the breadboard. Next, we'll be setting up a potential divider using a resistor and a LDR resistor. The LDR has no polarity, so it doesn't matter which way you connect it. For a potential divider, you have to connect it in series, and we connect the resistor behind the LDR connected by this common point. As the light changes, the LDR resistance changes, and this causes there to be a change in voltage, which is measured at this point. The Arduino measures the voltage at this point by using the analog pin, and in this case, the A0 analog pin. Next, we need to power the voltage divider component of this circuit, and to do that, we connect the resistor N to the ground of the breadboard. Next, we connect the LDR N of the potential divider to the 5 volts on the breadboard. We are now done with the input section, which is the LDR. Next, let's move on to the output section of our circuit, which is the LED. Before we connect the LED, let's first connect a resistor. This to ensure that less current flows to the LED so that it does not burn out. Next, let's connect the LED. Please note that LEDs have a polarity, and we have to connect the orange pin to the positive side of the LED, and this is connected to the pin 13 on our Arduino. The Arduino is the one that supplies current to the LED when needed. Next, connect the ground to the negative end of the LED and connect that to the ground on the Arduino.
Pause here to ensure that you have your circuit properly laid out before proceeding. As this is a very simple circuitry, there is not much content to talk about except to note that the resistance of the photoresistor drops when light intensity increases. We make use of the change in resistance to bring about a change in voltage in certain lighting conditions. This voltage change allows the Arduino to determine the values on which we can establish a condition to light up our LED. Here's the code that we have used. We have included the link to the code below this video where you can copy and paste it in your Arduino program and upload. It should work. Here are some points to note. 1. We left LDR readings from the changing voltage at different lighting conditions unpredefined with any integers because we are using it as an unknown variable that will be assigned a value when we read the voltage from the potential divider. Much like algebra finding x, this will make sense further down the code. The rest of the pins are defined as we are using them to assign digital pins. 2. Pin mode. There is only one pin mode we need to establish, which is the one for the output LED. This helps to set a proper 5 volts for pin 13 so that the LED is able to be bright enough when we call out digital write to output a 5 volts at the pin. 3. Serial begin. As mentioned, whenever we want to read and print out readings into the serial monitor, the communication between the Arduino who is reading and the display rate in the computer will have to be synchronized. By default, we use 9600 unless datasheet for components state otherwise. 4. Analog read. Now we have defined the data that is obtained from reading voltage of the potential divider as the unassigned LDR read. Analog read just helps to convert the voltage potential into readable data integers. These integers are important so that we can see the conditions in terms of numbers that determines what value represents a lit environment or a dark environment. 5. Serial print LN. It helps to print the data into the serial monitor for us to visually see them. You can monitor the serial monitor to test the threshold values at different states, the lit or dark environment. 6. If. For our case, our threshold condition in the lab is 30. If I switch on my lights, the number rises way above 30. If I off them, it goes below 30. It is safer to consider certain tolerance towards choosing the threshold condition to ensure a more robust system. As such, if the environment is dark, LED read will go below 30, so I will supply a digital write of 5 volts to the LED. The second condition would be that if the environment is lit up, LED read will go above or be equal to 30, so I will turn off the LED by supplying a digital write of 0 volts. Simple. Upload time.
Now let us move on to seeing our circuit in action. When it's dark, the LED in our circuit will switch on, and when it's bright, the LED in our circuit will switch off.
We can also connect this exact circuit to power up larger devices like garden lamps through a relay circuit. Feel free to look up online for more resources on automated lighting if you are interested. As users of the Arduino platform, there are times where you would like to further your projects into production or to have your projects in a much smaller scale. Some of such visions may not be realized with the use of existing Arduino boards. As we know, such boards are for you to prototype, meaning to convey what you wish to achieve. In actual productions, we either continue using microprocessors on a dedicated circuit board that has more specific and compact use, or we use a more simplified circuitry and components like 555 timers and transistors. In this last sample project, we will be using a NPN transistor, 2N3904, a 330 ohms resistor, two 1 kilo ohms resistor, an LED, a photoresistor, and a 7.4 volts LiPo power source. As this is an Arduino course, we will not touch on how to assemble this circuit. Nonetheless, the following video is good enough to get you interested and to show that it works. For those individuals who wish to build the circuits themselves, here's the circuitry. Unlike other online tutorials, you can get all the required items easily from our school's electronics lab. That's all, folks. We have come to the end of Mastering Arduino series, SUTD version. Time to roll out some credits. These individuals play a very crucial role in setting up this video. Please say thanks to them if you see them in school.